Hello. Timbits if you want any. Early comer special. Timbits if you want any. You're good? All right. Timbits if you want any. Behind you. Timbits behind if you want any for people coming in. Oh, yeah. Oh. It's funny how that's still week. Like, was it week 4 now? Something like that?
We got 10 more, including reading week. Not that you're tracking. Yeah, I'm not counting. Does that include 500? No, that's still exams. I thought there was 13 weeks.
Yeah.
So we have 9 more weeks?
Yeah. Timbits to your side.
10 plus reading week. Or sorry, 9 plus reading weeks. We've only got 3 weeks. We have 4 weeks.
Yeah, this is lecture 13. So 3 a week, so you've done 4. This is.
So we have 9 more.
Oh, Timbits there if you want any. You can help yourself. Yeah, and if you're quick, you can go pet the dog in the lobby. All right, so today we'll take a small detour and talk about libraries since they're kind of related to operating systems. And I guess no one's created libraries before, right? Has anyone created a library? No? Okay, like really weird, disgusted faces. All right, sweet. So we'll kind of learn about them today. So why are libraries important? Because remember, they're also part of operating systems, depending on what your definition of an operating system is. So for instance, we know for sure the kernel is part of the operating system, but like we said back at the beginning, Android and Ubuntu both use the Linux kernel. So are they technically the same operating system? Are they not really? The only difference is what applications run on them. And this is the typical kind of libraries you'll see on a Linux machine. You'll have the C standard library, and then you'll have other libraries built on top of it, like the system daemon library that's udev is run on just to kind of make it easier to talk to devices using the kernel. Then there's going to be a display server that actually renders stuff for you. And then on top of the display server, you could have a GUI toolkit built on top of it that uses the display server. And then you have a bunch of applications, and they might pass through multiple layers of libraries. So for instance, your network manager might straight up call the C standard library, it might call the system daemon, and it might not display anything at all. While if you have LibreOffice or Firefox, LibreOffice might just use the GUI toolkit, which would use the display server, which would use the C library, and Firefox might just use everything because you have it displayed to you. It'll capture your webcam, your microphone, talk to your devices, and do all that fun stuff. So we should talk about a bit about like good software engineering practice and what makes up libraries. So as you're kind of figuring out lab 2, right, just as an aside, the C has an ABI, which is a binary interface, and there's a certain convention for each individual architecture. So for x86 64-bit, you're discovering it's kind of also insane. By default, C is stack-based, where arguments are pushed in left to right order, and then there's caller saved and callee saved ones. But in 64-bit, some arguments might be passed in registers instead of the stack if they are simple enough. And I guess for lab 2, your thread stub code that you're creating just has 2 arguments that are simple, so they'd actually be passed in registers, which is kind of in the handout. But there's Wikipedia, there's lots of other conventions, there's fast calling conventions, and there's tons of other calling conventions, and just the caller and callee function just need to agree. And then some advantages that gives us, remember with system call ABI, we just are using 6 registers, and they're all a set size. So when we're calling system calls, there's only max 6 arguments, and they all have to be the same size, which is the size of a pointer. While if we're in C, we can have any number of arguments we want. They can be variable size and all of that fun stuff. Right, it just might be slightly slower if we're using the stack instead of registers.
So is C really just like the basis of everything?
So the question is C the basis of everything? And yeah, pretty much. We can figure it out. So like one lecture we saw, we could see every program that has the C standard library open, and it was all of them.
Right.
So C just makes things a bunch easier, but pretty much everything's built on the C standard library.
So no other operating systems kind of use another language, really?
Like each one will have its own C standard library that abstracts all the system calls. So you can use pretty much the same stuff, except for dealing with graphics hardware. That's different per operating system. So Windows will do its own thing, Mac OS will do its own thing, Linux will do its own thing, Android does its own thing. But that's the idea, is that if you have a C standard library and you write most of your applications you've written so far are just terminal applications, so you could run them on whatever you want because they pretty much just use the C standard library, right? So normally when you compile, it looks something like this, right? Everyone understands this. So if I have 4 C source files, When I compile them, they get compiled to a .o, which is just basically, it's an ELF file, and it's going to just have all the assembly code that implements that function and some information about what that function's name is, right? And then at the end, after you compile every single C file, you link them all together and kind of smush them all together to create an executable, and one of them has to have a main in it, right? We all have done this before and understand this. So static libraries are just a way to decompose it so you can reuse parts. So say of those 4 files, I know my util, my foo, and my bar files, I know I want to reuse them in different executables. So what you can do is you can essentially, link them together in an archive, which is basically just you smash a bunch of .o files together, and they just all live in that .a file. So lib.a will just be those 3 object files all kind of smushed together. And then instead, when we were linking our executable and we used each individual object file, we just link main with our library and then create an executable. So now if we wanted just to slightly tweak something and use otherwise the same libraries, we could modify our main file and link to the same library, or add another file, create a new executable for it, and use the same library, right? So we're just reusing things. Does this make sense to everyone? Because we're going to take a leap soon. Okay, so what we actually need to talk about, so static is just kind of copying and pasting. It's just one way to decompose what we already know, while dynamic libraries are usually used for more reusable code. So the C standard library that we kind of saw before is not a .a file, it is a .so file. And basically it's the same idea. A .so file is just a collection of .o files that you want to reuse, except there's a little special stuff that we'll see, so you can actually reuse it between different applications without having to link anything, right? And without having to recompile anything. So the fun thing is, if you have like 2 applications here, they can both use the C standard library, and then your operating system gets to do some fun tricks. So for example, if every single program uses it, so if you have 100 programs running and they all use the C library, well, instead of having 100 copies of the C library that are all the same thing, because we have virtual memory, one of the fun things you could do if you are the kernel is for each application that is using the C standard library, it would be at a particular virtual address, and then you could make each application's virtual address that corresponds to the C library correspond to one physical address. So they can all reuse the same physical address, even though they all have their own virtual address space, right? Because you pretty much just read this C standard library and execute it. You don't modify it, so you can actually share it between applications, which gives you some nice speed ups and benefits. So you essentially, if the C library is already there when you launch your application, you don't have to reload it or anything. It's already there. You get to use it essentially for free, which is kind of cool. Yeah.
Doesn't that cause a lot of data races or other stuff like that? Because aren't you all accessing the same memory?
So yeah, the question is, doesn't that cause a lot of data races? So yeah, so what's the condition for a data race?
Writing. So it's just code stuff.
Yeah, so condition for a data race, you have 2 concurrent accesses to the same location and 1 is a write. In this case, we're just reading and executing code, right? So there's no data races, it's all reading. We can have 1 billion if we want. All right, yep. Sorry? No, so the question is, does the dynamic library have to be compiled to an executable? And the answer is no. We'll see how to create the dynamic library. It's basically just a bunch of .o files. So we'll have an example that we can go through. So this is how it works, just to answer that question as well. So it pretty much looks the exact same as a static library. So all of these .o files that we would have had in our .a file, we just specify a different kind of linkage to the compiler, and it creates a .so, which is basically the same combination of .object files, just with some extra stuff on there, so it can actually resolve this difference. So the main difference is when you actually create your executable, you just link your file that has main defined in it, and then you just tell it what library you use. And then whenever you execute that program, your operating system will find the library and actually resolve all the symbols for you and do all the hard work, so you can just use the library, right? So every time you run your application, if you're using a dynamic library, as soon as you hit run, it will go find where it is and then start using it to call. Right, and that's the main difference. So you can think of the library as having the exact same functions. It's whether or not it's compiled into our executable or it's found at runtime and therefore can change, which is the difficult part. So some useful things if you want to see, what's actually using dynamic libraries, you can use LLD on all your executables and just double check. So let's see that. So I have some examples here. One of them is just called alloc example. So I can LLD it and see what libraries it uses. So we can see here it uses libc, and then on the right side of the arrow, it will tell you where that file actually is. So it's at user libc.so.6. And then here, there is this Linux thing that doesn't resolve to a file because actually the kernel provides it for us. So it's not even a real file, it's just something that looks like a library that the kernel provides for us, which is kind of sweet. And then there's this LD Linux architecture, and that's a library that does the dynamic loading for you and does all of the hard parts with kind of finding the library whenever you run it and loading it and all that fun stuff. So if your question is, hey, what uses the C standard library? I mean, I can use this tool on everything and see what everything uses. So for example, I could do it on LS. LS uses the C standard library. It also uses libcap, which, no cap. That's fun. We can do some other stuff. Cat. So LS is just written in C. Right? You could write LS yourself now. It wouldn't be that bad. Right? You kind of use stat in lab 1. LS just calls stat over and over again. And we know how to check what applications do, right? If I run user bin ls, if I want to see what it actually does, strace, right? We know all the secrets of the operating system now. So it writes out everything, opens a bunch of files. Yeah, so it opens a file called dot and then just queries what's in it. It does, get all the directory entries, and then it just prints them out. LS doesn't do anything that complicated, right? It has to use a system call, and we know how to monitor system calls. So if you want, you can figure out what system calls it uses and write your own version of LS if you really want. So that's fun. So you can also use object dump -t to see what symbols a library has in it or that are defined in an executable. So another example is today we'll see kind of our own memory manager a little bit. So I made a library called alloc, alloc wrapper.so. So inside alloc wrapper.so, I defined ralloc, I defined free, I defined malloc, I defined calloc, which we should know are all of our kind of memory management functions. Sorry? No, so this is in my library. So I have a file here called allocwrapper.c, and I just made a library that just contains that file. So I just defined 4 functions in it. So these are all functions. And then if you do -t on like an executable or something, so if I call alloc example, it'll tell you all the symbols that that executable needs to execute. So like, for example, this one uses printf, so it needs printf to run. So you can play around with libraries like that. And of course, there's our fun object dump -d if we want to see, you know, what the code is within a function, which might be useful for lab 2 because it's kind of messy. All right, so to go on to the fun thing, so the main difference between static and dynamic libraries is basically whether or not that code is included in your executable or not. So big drawbacks to using dynamic libraries, the big drawbacks of using a static library is that you can't reuse a library anymore. It essentially just copies and pastes that code and puts it into your executable. So if you have 100 programs using libc and they're all statically linked and they all use, for example, printfs, then you would have like 100 copies of printfs just running in your system, which you don't need to. So it will actually waste some space. And then the other real big drawback is that if you use, if you want to update that static library because it's included in that executable, well, if you just update that static library, the executable doesn't change. So if you want to update it, you have to recompile it, right? So given that, what might some issues be if we use a dynamic library then? Yeah. Yeah, so that's one thing. So if the API of the dynamic library changes, it might screw up our thing that already works. So it might break our already running application. Were you going to say the same thing?
Yeah, like if you make an update that crashes your program.
Yeah, so you could also change the behavior of the library and then suddenly your application doesn't work. And there is a third, even more subtle, worse thing is you could change the ABI and you will probably not realize you've done that. So we'll have an example of that because that is the fun one. So let's just go into the example. Okay, so we like kind of know how to write correct applications, right? We write good code. So I'm going to have a very, very, very simple application and make a library. So say I want to make a library that represents a point. Points are simple, right? They just have an X and a Y. Pretty simple. So I will define, so in the library, it's just a collection of functions. So I will go ahead and say my library consists of 4 functions. So the first one, I'll make it point create that returns a pointer to a newly created pointer, and it has 2 fields, X and a Y. So you expect if you create a point with an X and a Y, then its X is set to the first argument, its Y sent to the other argument. And then it's going to become clear very shortly why I'm using a pointer and kind of hiding the struct. So in this case, for this library, I just say struct point. I don't say what's in it. I hide the details from the user and just let them be none the wiser. Then I'll have like a getX function that just takes a struct pointer, and then a getY, and then a destroy, which should just free it, right? So my library consists of these 4 functions. And here, I'll show you version 1 of the library. So this is going to be the entire contents of the library. So the library itself will have 4 functions, and these are the implementations of it. So in here, I will include libpoint v1, and that is just saying what the struct actually is. So this struct is going to start with a Y and then an X. Those are the 2 fields it's going to have, right? Makes sense. So that's the only thing that is in that. And then inside here, I just have point create that mallocs the size of the struct. Like accesses the struct's fields to set X and Y to X and Y. Makes sense. And then I just return a pointer to that. And then in get x, I just access x and return it. Get y, I access y and return it. And then point destroy, I call free. So any questions about this? Pretty straightforward library, right? Cool. All right, let's see how straightforward it actually is. Path equals. All right, so in my point example code, I'll just, include my library, and then I'll compile it. So now there's a file here called libv1, and it's just called libpoint.so. So that's where my 4 functions are. So create, get x, get y, and destroy. So LD library path, so that's just saying use the library that's in that directory. So this is my v1 code. So in the point example, I go ahead and I just use point create, and then if I print out the point using get x and get y, then that's all good, right? It's kind of what I expect. So any questions on that? So within the point example that just contains the main, the only thing that's compiled in it is point create, like the call to point create, and then point create's defined in that library. So everyone on the same page, because things might get weird soon. Okay, so someone might come along and say, hey, dummy, why is it x, y in this struct? Like, I should be able to change the fields around, right? And do x, y instead? That seems like it makes more sense. And then it's like, well, it's not going to change any APIs, right? It still has an x and a y. I just changed the order. So APIs aren't going to change. All the names are the same. Everyone agree with that? That this change shouldn't really matter. So just to show it really doesn't matter, my libpoint v2 code is actually exactly the same, right? Line for line, or character for character, it's exactly the same. The only thing I did was change the orders of the struct. So now, when I execute this, because I'm using a library, I get the nice, I get the output I expect, which is good. But now I will show you what will happen if you expose the struct to the user, then it would look something like this. So if in the header file, you gave the definition of struct, then in whoever is using the library in their code, they will be able to use that struct, and then I could be like, hey, these function calls are stupid. Like, why don't I know it has an x and a y, why don't I just compile that in there, right? Which should be faster. I don't have a function call or anything, right? So that makes sense to me. That makes sense to everyone. That should be the exact same thing.
Wait, so what are you doing differently here?
So instead of calling, point get x and point get y, I'm just assuming that library exposes a struct to me. I'm just using the struct directly.
Okay.
Yeah, so I'm just going to use the struct directly. Cool. Well, should that be the same thing? Yes, or different? Since I'm showing to you it's different? Okay, well, I don't break the world, so if I do the same thing, it's the same, right? So I'm using version 1 of the library, and I'm using version 1 of the struct. It's compiled in my executable, so they both agree it's all good. Well, then the question is, what if I do that and update my library? And then say you were actually depending on this because we embedded all the code in our executable. Now what's going to happen? Yeah, now the order's swapped. So, and all I did was say, use the other library. Anyone want to explain why that happened? Because I didn't change the API or do anything. I just changed the order of the fields in my library, updated my library, and just said, yeah, that's fine. Yeah.
Maybe like the order in which you did it
Yeah, so the answer was the order which I declare it actually changes where it is in memory. So structs in C have a very predefined memory layout, and they're guaranteed to be ordered in memory in the same order they are in the struct. So in version 1, so by C standards, it's going, an int's 4 bytes, right? So by C standards, if you read the real boring documentation, it will say that this struct is going to be 8 bytes, and all the fields are going to be in the same order they're defined. So at, offset 0 is going to be Y, and at offset 4 is going to be X. While in version 2, I swapped it, right? So now X is at offset 0, and Y is at offset 4. So then here, if I go back to my libpoint example, if I embed it like this, and I use version 1 of the struct, well, it's going to think X is at offset 4, and then Y is at offset 0. But if I use version 2 of the library that calls the point create with version 2, it's going to create a struct where it assumes that X is at offset 0, and then Y is at offset 4. Right? So just swap them around.
So you're using 2 libraries here?
So in here, I'm using the library call to create the point always. So it will be whatever library I use. So like if I do LD library path L2, it'll use version 2 of the library. If I use V1, it'll use version 1 of the library.
Okay.
And then, so point create will always use the current library, and same with these functions. They'll always use the current library.
So then why is your other thing using the previous library?
Yeah, so this one's, so I can have both, right? So it's just using, it's kind of simulating what would happen if you actually just compiled in that struct in your application. So if the library defined the struct, you might use it in your application, and then when you compile it, the offsets are going to be whatever they were at the time when you compiled it, right?
So the library itself has different offsets than the struct that you compiled into the executable.
Yeah, so the difference between the two libraries is the offsets within the struct, like I swapped the fields, right? But if I just use the struct directly in this executable, it'll have whatever I embed in it, right? So here, I'm using V1 of the struct and then accessing its fields. So no matter what, because the version 1 of the struct doesn't change, this is always going to be offset 4, the X, and then Y is always going to be offset 0. And then if I interpret it as version 2 of the struct, X is going to be offset 0, and Y is going to be offset 4. So those two lines, oops. So it's like, this is what happens if I use the library. This is what would happen if I compiled this executable with version 1. This is what would happen if I compiled the library with version 2. So that way, if I use, right, if the library I use matches what I compiled with, I'll always get the right number, right? So if I use V1, now this one matches. But the point is, in either case, if I actually use a properly encapsulated library that doesn't say where the struct is, right, this using library one is right in both cases. It's never wrong because it only uses what's in the library code. So that makes sense that even changing, so if you make libraries, you have to get these details right, unfortunately. Otherwise, bad things can break. Because imagine if somewhere in the C standard library, someone did this to you. Do you think you could debug it? Right?
The solution to it is just to use actual function calls rather than access the...
So the solution to this is if a user knows the layout of a struct, you are not allowed to change it anymore. Like if you expose a struct to the user, so like in C, right, that you have like the stat struct and a bunch of other structs, if they ever change even the order of the fields, they would break pretty much every single program in existence.
Wait, who was in charge of that?
what? The C Standard Library Committee. So this actually happened, I forget what year it was, like not that long ago. They broke an ABI in the C Standard library, and the only fix to that is to recompile everything, or else things just broke in very mysterious ways that were impossible to debug.
Wait, there's like an international committee that controls the system.
Yeah. Yeah, because you have to all agree, right? You can have different implementations of the C Standard Library. If they don't work, or if you change fields, no programs are going to work anymore. So this should make everyone amazed that computers actually work, right? Because even if you change just that little subtle thing, things break. You would, trust me, you think data races is hard? This is actually worse. I guarantee you will not be able to debug it. So here's our example, right? Even if we change the ABI, and if we don't understand how programs are compiled, we might not understand the ABI and what actually changes the ABI. So like one very common thing that will break it is just changing the orders of things in the struct, right? It doesn't change our APIs or anything. But it does change the ABI, in which case your whole application, right? Anything that uses your library can suddenly break in very mysterious ways. So like if suddenly I updated a library and then, that was using the points and then everything got flipped around, that would be really hard to debug. Imagine you updated some game or something and then your screen was flipped upside down. Like, good luck, right? So here's that. So just to point out that C does have a consistent ABI for structs. That's why it works, and that's why everything agrees that if you see the struct, you know exactly where the memory for everything is. And then the only way anything works in computers is literally if everyone agrees to do the same thing. If someone doesn't do what you should, then systems just don't work. Again, it's kind of amazing that things work. So here's that example. So any questions about this example? And
So why don't the Linux system calls, like we use the system library, so why did they allow us to access the structs? Like why did they just let us use getters and setters?
so it's slower to use a function call, and they are a committee, and they're saying, since we gave you the struct, we will never change it. So that's why if you look at, one of the golden rules of the Linux kernel is you never break user space, and there's a lot of structs floating around. So if you want to add a new feature or do something, and you just have to create a new struct.
That's why there's so many just random structs, because
Yeah, you can't modify them ever. That's why you'll see there's git PID, and then there's git PID2, because they doubled the size of it. But if it's in a struct and you double the size of a process ID number, you have to have a new struct because it suddenly doesn't line up anymore, right? So that's why if you look, especially at x86 kernels, that's why you'll see multiple copies of the same function call, because they're all going to use slightly different structs, right? If I change the size of a pointer or of a process ID from 32 bits to 64 bits, I have to change everything that involves that. Right? I change the size. Yep.
So you said this happened a while, what was the result of that?
You have to recompile everything.
So almost every computer in the world has to recompile stuff?
Yeah, it was like a Linux-y one that, I think it was C++ actually, where they changed the ABI in the list by accident. So if your application ever used standard list, it broke. And the only solution was to recompile everything. And that's a big pain in the ass if your C compiler also uses that and you can't recompile the C compiler because it's that. So yeah. So yeah, and then that's really bad too if you're using a Linux system and you get partial updates. So when I was updating my computer, half the packages were updated, half them weren't. So half of my stuff just didn't work anymore. That was a fun month. But yeah, it can happen, and if you do it in the rare case, but they've only done that like once or twice in 30 years, which isn't that bad, but it's terrible. Yeah.
So if chaining the API is so horrible, why don't we just have a ton of stuttering error functions to like abstract the build error?
It's slower.
But is there a way you could like make the compile work?
You can't optimize it away because optimizing it away is the same thing as knowing about the struct, right? So it's unfortunate. So unfortunately, if you want things to be fast, you have to pay the tax, and this is one of the taxes, right? The alternative to this world is living in a world where your operating system and whole thing is written in Java, and that would be terribly slow and no one would use it. I guess if you use Android, but Android sucks. So, sorry. They don't use Java that much. The core operating system of Android is not Java, so it's not that bad, right? All right. Ooh, I didn't think I'd say that. All right, I didn't say that. Don't worry about it. All right, so to get rid of this problem, there's something you can do, which is just kind of a contract between developers called semantic versioning. So if you use something like that, it says, hey, if you have a version number, just have 3 digits. Do major digit dot minor digit dot patch digit, and then increment them in the following way. If you break something that is incompatible, you change the API, you change the ABI, you do anything like that, increment the version number, like the major number. So if you go from library 1 to 2, that means you can't reuse it, you have to recompile. And if I just get a random update and it breaks my application, I'm going to be mad. But if it goes from 1 to 2, I can be like, oh, okay, well, I'll just recompile it, and then I can use the new library. That's fun. Then you increment the minor version if you add new functionality in a backwards compatible manner. So you add a new feature, for example. So I added a new function. I didn't touch anything else that's existing. I just added something new. Then you would increment that number. Then for the patch number, you should increment that if all your functions, all your APIs are exactly the same, and you just do some normal bug fix. So, you know, fun story to try and make everyone follow good practices. This is how my slides are versioned. So I increment the minor version if I just fix text on a slide or reorganize a slide, but all the slide numbers are the same, so I don't change the slide numbers. I increment the minor version if I add a new slide, so the slides might not correspond exactly. And then major version, I just increment every year when I redesign stuff, right? So even your slides follow a number. So if you look at your, like what slides you have downloaded, and then you check what I have, right? Given the difference in version number, you should know what to expect. So, you know, if I'm showing you, if you have 1.0.0 downloaded and I'm showing you 1.0.1, that means I like screwed up something on the text of one of the slides and I fixed something, right? So you should follow that, and that makes your life a lot simpler than just, hey, I changed something, good luck, maybe it'll work, maybe it won't work. So also the funny thing about this is, so if you go off the Linux kernel's primary rule where we don't break anything ever, well, in that case, the major version doesn't matter because you never break anything anyways, and then you would essentially just increment the minor version. And if anyone's ever followed the Linux kernel version numbers, where we just went from 5 to 6, the rule for that is if the lead developer runs out of fingers and toes for the minor number, he increments the major number. That's it. So that's literally the rule. I'm not joking about that. So if you don't break stuff, then you don't ever have to increment that. Well, libc is like on version 2.2 or something, so they broke it at one point, which I think corresponds to what I was talking about. All right, so the cool thing about dynamic libraries, because they're included at runtime and resolved then, is you can do a bunch of fun stuff. So I kind of already used LD library path to change what library I used when I ran the executable, right? I never recompiled it. aside from when I added code to it. So if I have the following example, this really simple program, it just runs malloc, prints off what is in, what the value of the pointer is and frees it. So if I run this, I should just see x is equal to some random memory address, right? So let's go ahead and do that just to make sure we're all good. Malloc exam. So I just get some random memory address, right? Changes all the time. Cool. So say I want to be like, hey, I want to implement my own Valgrind. Cool. I'll just, I'll essentially just overwrite malloc and free and just start monitoring them. So I went ahead and wrote that because it's actually really short. So, and then I can use LD preload to say, hey, load this library before anything else. So in this library I wrote, I defined malloc and I defined free. And I have some implementation for them that essentially logs and then calls the real one to do the actual work. So if I do that, I get to monitor my program, and this is essentially what Valgrind does, right? So I can see I malloced 4 bytes. Cool, I got this pointer that was 2A0, which matches exactly my X call. And then I called free on it, and it matches that pointer too. Anyone confused by something here? What? Yeah, what the hell is this? So I'm literally just monitoring all the calls. So if you look at this, right, it looks like I malloced a kilobyte and I never freed it. I have a memory leak, right? But what I wrote, I just wrote malloc and free. What the hell? Anyone guess what the hell is going on? Yeah.
Would it be for the actual programming for the library itself from allocating some space for that?
For what?
The library itself?
No, so the answer might be, is it for the library itself? And the answer is no, because the library is already loaded, right? By the time I call malloc, my first malloc. So it's already loaded at this point, and the big malloc didn't happen yet. Yeah, so it's the print function. So this actually gives you some insight as to what print does. So that malloc is actually internal to print. So print creates a little buffer because it needs to essentially copy this string in and then find the %d and replace the bytes with the value for x, right? So that malloc is actually printf's buffer, and we can see it now.
So printf doesn't free the buffer?
Yep. So printf printf is not doing what we said we should all do in free, right? But printf never frees it. But anyone guess why it might not free it?
Program exits? Yes, so we don't care.
Yeah, the program exits so we don't care. Also, another reason, yeah.
You're reusing it?
Yeah, it would reuse it, right? Why would it malloc free? Like, it's going to malloc every time you call printf. Seems like a waste of time. So optimization, just malloc a buffer, keep on reusing it over and over again. Yeah.
So if you're using like printf, right, and you run a Valgrind, will Valgrind show that you're leaking memory?
So wait, do I have it installed? Yeah, I do. 2 allocs, 2 frees.
So the free is getting called after return or something like that.
Nope. So this is why you use Valgrind instead of doing it yourself, because there's special cases. So if we do that, so if you look at the Valgrind documentation, it says, the C standard library, which is used by all programs, may allocate memory for its own usages. Usually it doesn't bother to free that memory when the program ends. There would be no point since the kernel reclaims all the process resources when it exits anyways, so it would just slow things down, so why bother? So they know that, and they'll specially handle that case for you because it doesn't free. So Because if you ran, if you ran Valgrind on this, and right, if I ran Valgrind on this and I got 2 allocs and then 1 free, how the hell am I going to free the other one, right? It's going to give me it's going to tell me I have a memory leak that I have no hope in solving ever. So this is why you wouldn't write your own one, because there's a lot of stupid special cases like this. Yeah.
A few questions. One, why do we ever need to free anything? And then 2, if you are to write into printf something larger than 100 or 1024 characters, does it just mess up? What happens?
Okay, first question, does that mean we never have to free anything? Let's see,
Yeah, I see the note. But
So if you don't have to call free if you know it's going to live for the whole duration of your program. That is fine. But if it just uses the memory for a bit and then can free it and then use it for other stuff, that's better. But so you have to, if you want to keep it alive the whole time, you have to argue that it should be alive the whole time and that you know of that. And right, so you can't get away for your thread example. And then let's see if we make this bigger. I don't know the easiest way to make this bigger. How would this explode really quick? If I just type like 1,000 characters, like.
copy and paste.
Let's see if that's long enough. Warning. There's no equal sign. Oh God. Yeah, there's still an equal sign. Do I have to make it one line? Missing terminating character. Yeah, I do. Oh, geez. This better be worth it.
Oops. Why does it have to be one line?
Because, see, there's a better way to split it up. You can do ending colons on each line, but I'm just doing this freehand, so there we go. What do you want? You want me to run it again? Jesus.
So why doesn't it?
Oh, it's not that big. I didn't reach 1,000 yet, but you can do this later. It'll probably malloc another 1,000. Yeah, probably just double the size of the buffer.
Okay.
Yeah.
So for LD preload, is it basically first takes precedence in terms of you define malloc in the LD preload and then it won't use the next definition of malloc, or how does that work?
Yeah, so the question is, what does LD preload do? And LD preload forces this library to get loaded before anything else. So in this library, it has malloc. So I force this to load and load first, and then since it has malloc, it will point to this malloc.
And then what happens when you run into the malloc defined in standard library? Will it just not use that definition at all?
Yeah, so this is super implementation. So I'll show my code. So my code is actually this. So this is my malloc function. So this is super hacky. You never need to understand this. But this will essentially be like, okay, I'm malloc, you call me. Find the next malloc, that's not me, and then I'll call the next malloc, and then I just print off some logging information. So you can do some funky stuff with this if you understand this. But this is like, this is one hacky way you could implement Valgrind if you want, right? So if I just use my malloc wrapper and keep track of my mallocs and frees, I could actually line them up to see if you have leaked memory yourself, right? But then I'd have to have special cases. If there's a malloc in C standard library, just ignore that because you'd never free it anyways.
So you just always assume that C standard library is perfect, or?
Yep. Yep, you just pretty much always assume the C standard library is perfect. Otherwise, your life's terrible. You also assume compilers are perfect.
And they're not.
No, my research was in compilers. They don't work. Well, there's like very subtle bugs. Compilers are very good. So fortunately, compilers are very good. The C standard library is very good. The Linux kernel is very good.
Why?
Is what? Rust is good.
Is Rust based in C?
No, Rust is written in Rust. So most languages write. When you get to compilers, the fun thing to do in compilers is always write your compiler in the language you implement in, and that's the compiler course. So if they let me teach you that compiler course, I'll teach you about that too. It's lots of fun. But anyways, for today to wrap up, we learned dynamic libraries, comparison to static libraries, how to play around with the dynamic loader, and an example of breaking the ABI, which completely screwed over our application. So just remember, I'm pulling for you. This is our world now, right? Thankfully, people are good at writing code, so, and hopefully you will be too. So I'm pulling for you. We're all in this